We present TVConv, an efficient translation variant convolution for layout-aware visual processing. Efficiency matters for AI-powered applications, especially when the cloud server is out of reach and the computing is done locally on mobile or edge devices. Despite various networks being proposed for efficiency, their fundamental operators remain more or less the same as convolution. It works by applying filters in a sliding window manner, making it translation equivariant. There are a series of filters for various feature matching. We claim that this translation equivariance is inappropriate for many layer-specific tasks. For example, face recognition, defects detection, brain MRI analysis, optic disc cap segmentation, etc. We observe that these tasks naturally exhibit the properties of large inter-image variance and small cross-image variance. We illustrate this by calculating the statistics of the intermediate VGG feature maps. These two properties together provide room for efficiency improvement. To achieve that, the first step is to make the convolution translation variant. When the filters are applied to a specific location, only a small portion will be activated, and for different locations, the activated portions can be different. This corresponds to the large inter-image variance. Given another input image, the overall activated pattern would be similar, corresponding to the small cross-image variance. By collecting the activated filters, we let the filters be translation variant. Compared to the original filter block, now it's much thinner and consumes less computation. However, naively doing so results in an unaffordable number of learning parameters, as the image size can easily grow up. This impedes efficient chaining and may be prone to overfitting. Therefore, step 2 is to reduce the number of parameters by using depth-wise convolution, followed by filter decomposition. To further strengthen the translation variance, we decompose the filters into compact learnable affinity maps together with a weight-generating block. To this end, we propose TVConv. The affinity maps are used to generate weights of the filters, which are then applied to the image feature map to get output. TVConv is translation variant and shared across images. Here is a more detailed framework. The affinity maps depict pixel paired relationships gracefully and are automatically learned from the training data. For testing, the weight generating process can be performed only once as initialization. The weights produced are then cached in memory, allowing them to be fetched efficiently for subsequent computings. We compare TVConv against the static convolution, per image dynamic convolution, and per pixel dynamic convolution in terms of the translation and sharing properties. And we claim that only TVConv fits into the layout-specific tasks. Although conceptually simple, TVConv significantly improves efficiency. For face recognition, we replace the depth-wise convolution with TVConv in both the MobileNet V2 and ShuffleNet V2. We then compare the accuracy versus complexity trade-offs. TVConv achieves 2 to 3 times speedup without accuracy drop. On the other hand, TVConv boosts the accuracy by nearly 3% under an extremely low complexity constraint. We rigorously compare with many other operators and show that TVConv strikes the best accuracy and complexity trade-off. This gap is consistent when we measure the accuracy throughput on a Raspberry Pi. TVConv consumes a medium amount of memory, less than the per pixel dynamic convolution and self-attention variance, but fairly higher than others. We visualize the affinity maps from shallow to deep layers. For medium layers, they progressively learn meaningful layer information, while for other layers, they look more abstract. We conduct further experiments on the optic disc cap segmentation, showing that TVConv achieves more accurate and resilient results. For more information, please refer to our paper and codes. Thanks for watching.